Question number 4 is the continuation of question number 3, but this time you need to determine the diameter of the bottom part with the condition that the shear stress in the assembly would not increase. The overall shear stress would not increase. So the question number 3 is given at the side. Well, let's take a look. The thoughts are accepted on the pulleys A and B, and knowing that each shaft is solid, determine the shear stress in shaft AB and the shaft BC. So this is question 3. Previously, we need to determine the shear stress for the portion AB and then for the portion BC. And we are given the diameter of the bottom part of the shaft. Now, let's come back to question number 4. And we need to calculate the diameter. We need to determine the new diameter of the bottom part so that the shear stress of the top part of the assembly, so that the shear stress for the overall assembly would not increase. The maximum shear stress would not increase. Okay, let's look at the solution in part 3. Let's look at the previous solutions of part 3. Now, the previous video showed the shear stress of portion AB was 56 megapascal and the shear stress for the portion BC was 36 megapascal. One part of the assembly is showing you a higher stress than the other part. That is to say, the failure of the whole assembly is governed by the top portion because it has a higher stress. Then let's look at the equation we used in the previous video for question number 3. Tau equal to 2c, 2 times of the top, divided by pi r power 3. The radius is the lowercase r, and we use a value of 0.023 previously. Now, if you use a smaller radius, if you make the bottom part of the shaft smaller, if you start to decrease the diameter, the radius, then you are going to expect the shear stress is going to increase. That is okay, because that is what we need to do for question number 4. We need to recalculate the radius of the bottom shaft, and we are expect to use a smaller diameter. Now, that will increase the stress. The maximum value of the stress that we could use is going to be this value, which is equal to the stress value of the top portion of the assembly. Okay, by doing that, we are going to make sure the stress value in the whole assembly, in the overall assembly, would not increase. Yes, we are going to increase the stress level at the bottom part, but as long as the recalculated stress value of the bottom shaft is not exceeding the stress level of the top portion, that will be fine. Okay, let's calculate that. Tau equal to 2c pi r power 3, and the previous torque diagram is given here. This is 700 Newton meter. So we are going to apply 700 to the torque. The torque value, the value for the tau, the shear stress, it was 56.6 megapascal. That is exactly the same stress level of the top portion of the shaft. Then we will recalculate the radius. That is the only unknown in the equations. That will give you a value equal to 0.01969 meter. Okay, diameter is twice the radius, so that will give you 39.8 millimeter. That is the recalculated diameter of the portion B to C, and that is the minimum. Making it smaller than 39.8 is going to exceed this stress. If we start to exceed this stress level, that means we start to increase the stress of the overall assembly. By limiting it to 39.8, we are going to make sure the stress level in the assembly will not increase.